Yeah, that's an open question. So whether or not I will prove the Siegel's theorem, I mean, I will not prove it. Siegel proved it. But whether or not I will give you the proof is something I haven't decided yet. So I don't really know whether there is an easy, a doable way to present the proof. I need a little time to think about that. Yeah. So if we do not do the proof, at least I will give you the idea of how this is done. Yeah. Then I want to mention some of the other related results to this. So, for example, there is a result of Landau which says that, so there are three results that are quite important in this, classical results that are important. These are results of Landau, of Siegel, Landau-Page, and Estermann. And but if you hear the names, you see that these are very old results. Yeah, these are very old results. There is one result which I said effective result. There's a result by a contemporary mathematician Tatuzawa, but it is not a complete result. It's under certain assumptions. Yeah, and at the end, I will give you a conditional result as to when Siegel zeros will not exist, and this will pass through the question of the Goldbach problem. Yeah, it's not an unconditional result. It's a result that will say that if certain things are true, then the Siegel zero does not exist. Yeah, and not the other way around. Not that if the Siegel zero does not exist. Yeah, so yeah, so let me give you a result of Landau. So theorem. So if I take 2 constant positive C such that if chi1 and chi2 are quadratic, modulo, two different moduli are possible, q1 and q2, and if I take the product chi1 times chi2, you know that I can take the product. If this is non-principal, that is, you mustn't choose chi1 and chi2 such that the product becomes principal, then Ls chi1 times Ls chi2 has at most 1 0 such that the 0 is written as beta plus I gamma, 0 beta, such that beta is less than 1 and greater than 1 minus C upon log Q1, Q2. So what does this say? How should you interpret this result? This result says that if I take a product of two L functions, where chi1 and chi2 are quadratic, even if Q1 and Q2 are different, then the product of the L functions will also have at most 1, 0 in this region. For that also you'll be able to find a constant. All right. Now, do you remember that last time, yesterday, we did a theorem which said that L1 chi was not equal to 0. Yeah, the fact that L1 chi is, so we can use the fact that L1 chi is not 0, but we can also use the fact that individually, if I take a function Ls chi 1 and Ls chi 2, each of them can have at most 1, 0 in the good region. Yeah. So if so, since there is at most 1, 0, so again I'm giving you a sketch. Okay. So that means that you cannot have beta 1, beta 2. You have, if there is beta 1 and beta 2, so beta 1 will come from, for example, Ls chi 1, okay, and beta 2 will come from so the idea is this proof is not so difficult. Yeah. So since there is at most 1, 0 of each of the L functions, you can assume let beta 1 be 0 of Ls chi 1 and beta 2 of Ls chi 2. Okay. We said that there exists a constant C. We will let this constant to be small. Okay. We can say that if the constant is small, how small? So you can choose not really, yeah. Let beta I be between something, some alpha and 1 for a suitable constant. Now, why can this happen? You see, if C is small, yeah, then beta is between on one side it's less than 1, and on the other side it's you are closing in the gap if C is small. Yeah. So then you can use some result on L prime by on use bounds for L prime by L and zeta prime by zeta, and this should give you a result like that. Yeah. Would you like to try that? Yeah. You can try that yourself, and we can see if you are capable of doing that yourself. And yeah. So do you think we could break now? Because I mean, we can do a little longer in the afternoon. Is that okay for you? If we break now and have a longer session in the afternoon? Is it okay for you? So it's 12:30. No, I mean, if I stop now, then we can go a little longer in the afternoon. And so what is it? Whom is it bad for? No one. Okay. There are some ratios to be, some ratios to be respected. Okay. So yeah, because now if I start saying something, I have to start saying something that is new. And that's not a very intelligent idea to start something. Yeah. Yeah, but who's going to think about that? Yeah. Okay. So you can think. You're allowed to think. Okay. And then the part of the complex. You see, when we did the first part, the chi being complex, when we did the zero free region, then I said there was one part which was going to be complex. Yeah, okay, I can give you some ideas of how that is done. Yeah. So some hints on that part. Yes. Yeah. Mm-hmm. Yeah. You have to find something else. There is no formula for it. Okay. So it's not an algorithm. Okay. It just happened that it was true for a certain theorem. It's not an algorithm. All right. So, but there is one thing that you should notice, that yeah, here you can assume what you know already. I mean, not assume. You can use what you know. You know Siegel's. For example, Siegel's theorem. If you like, you can use that. Okay. So let me talk a bit about this. Let me talk a bit about this complex. The zero free regions. Yeah. The part that we left as so complex zeros. Yeah. Not complex zeros. Complex chi. That's the part we left. Okay, so I suggest, okay, that first you prove this. Mod Q. And if sigma is between 5/6 and 2, then L prime by L S chi is equal to E0 chi. I'll tell you what E0 chi is, upon S minus 1 upon sum 1 upon S minus rho, where rho runs over all the zeros, and plus an error term O log Q tau. Okay, so for which rho minus 3 by 2 plus IT is less than equal to 5 by 6. And what is E0 x? E0 chi? E0 chi is equal to 1 or 0 depending on whether chi is equal to chi 0 or chi is different from chi 0. All right. So maybe you can begin by proving this, and then we can continue to the rest. This is a result that you might need, and after that, if you decide to not use it, anyway, you have done this. That we might need for the complex guys. So can you try to prove this now? We can do that. That can be something that okay. Or if you assume this, this is one thing you can prove. Then another one that you can prove is to prove that if sigma is greater than 1, the real part of this will all help you get the bounds, yeah? Minus 3 L prime by L sigma chi 0. Thus, perhaps you will see why we are doing minus 3, minus 4 and things like that. L prime by L sigma plus IT chi minus L prime by L sigma plus 2 IT chi square is greater than or equal to 0. Do you have some idea about, oh, there should be some bracket that closes somewhere? Yeah. So do you have an idea where those 3, 4, and 1 are coming from? These are from trigonometric identities. You remember? Yes? Yeah, exactly. It's because these are things that come from the, for the Riemann zeta, it's you find this logarithm, these cosine functions coming up, and that's where the 3 and the 4 come from, 3, 4, and 1. Yeah. So this is the second thing you can prove. I'll give you some more things to prove so that you don't feel idle. And here, 3, prove that this is the Euler gamma function, gamma z. Prove that this is equal to log z plus big O of 1 by z. When is this true? For this z, which is going to infinity, and in a certain angle. And where is that? If the argument of z is between pi minus delta and minus pi plus delta for a fixed delta greater than 0. You can prove this. Yeah. Fourth, it's another question concerning the Euler-Gamma function. These are nice exercises. They help us understand and use certain techniques. You can log of gamma z is equal to z minus half log z minus z plus half log 2 pi plus an integral u minus u plus half. Does this remind you of something? Does this last integral remind you of something? You probably saw something like that for the Riemann zeta. You take the half part out and then you use a contour integration. Yeah. So that's another question you can think about. And yeah. This is the fourth question. Yeah? So you can start thinking about that.